So I will tell about some recent developments, but I'll start with some of the not so recent developments. So first of all, you're worried I will go straight into ergodic theory, the familiar theorem, take a deep breath, Semeredis theorem. I expect everyone is familiar with it, but I hope my notation is confusing. So this was proved in 75, but 12 years earlier, Furstenberg, just purely by working on dynamical systems with no view towards proving Semeredis theorem or anything of the sort, structure theory for Diesel systems, which is a class of systems, logical dynamics. And so when he learned of this statement, Furstenberg more or less saw apparently right away how to use his structure theory, or rather to adapt it to measure preserving systems and give an ergodic theoretic proof of Semeredis theorem. So he proved this theorem 2 years later. And so an immediate unpleasant feature of this statement here for an ergodic theorist is that there's a limit there. But so this raises the question, does this limit exist? And we'll come back to that later. But so for now, I hope it's clear that this statement does imply Semeredis theorem. So let's go a bit over that. I should say this notation just means averages, so that there's a finite set I'm averaging over. You sum and you divide by the number of elements. And so you take an n for which this is positive, and then you take an a in this intersection, a little a, and you get your, your arithmetic progression inside your set A. But this theorem of Furstenberg gives something else that I don't think follows directly from Semeredis theorem. It gives us that if you give me a set A with positive density, then I can find some L, some length, such that any interval of length L, as far as you want in the integers, will contain the common difference n of an arithmetic progression inside A. Okay, I should put a quantifier on k here. So you give me a set A and the length of the progression k, and then depending only on those two parameters, you can find an L. And so this also raises potentially the question, how does L grow as density of A goes to 0? So these are two questions that may come to mind when you see this theorem. And so ergodic theory is suited to answer the first type of question. Do limits exist, limits that should exist for some reasons? And so in ergodic theory, we like these types of questions. The second type of question may appeal to a lot of people in this audience. It's not something I expect ergodic theory could say much about. So it's some sort of quantitative relation between these parameters. Ergodic theory is not very well suited to answer this. So so in any case, this statement is slightly stronger, arguably, than Semeredis theorem, but this is not the main reason why Furstenberg's approach is so interesting. It is because it's versatile and it allows us to prove many other related results. So just 1 year later, Furstenberg and Katz-Nelson proved the multidimensional Semeredis theorem, which is the theorem you see here. If you've never seen this before, I can just explain what happens in Z2. So you take a subset of the integer lattice in Z2, which has positive density, 1% of all the points in Z2. Then any constellation you can find, any finite set, you can dilate and shift and fit it inside your sparse set you started with. Or, well, small set, but with positive density. And so this was proved in 1978 with ergodic theory. It was similar to the proof that Furstenberg gave for the one-dimensional version, that there are some additional complications. But the first non-ergodic proofs only appeared in the mid-2000s. So I think there's a paper of Gowers. I don't know if that was the first one. So there was quite a gap here. But of course, the point is that the ergodic theoretic proof will not give you any bounds or any good bounds. All right, so all the theorems mentioned here, Semeredis, the thing with the gap L and the multidimensional version, they are all generalized by something called the density Hales-Jewett theorem. So the Hales-Jewett theorem was something about colorings of products of finite sets. So I won't give you the statement. And there was a density version that was easy to formulate, but not so easy to prove. And then Furstenberg and Katz-Nelson in 91, they found a proof of this result using, again, ergodic theory. And non-ergodic proofs of density Hales-Jewett are now available thanks to the first polymath project, which is why Mr. Polymath's initials are DHJ for density Hales-Jewett. I should also point out that even though this is a non-ergodic proof, the one given by Polymath of density Hales-Jewett, it comes with rather poor bounds. So there's still a question here of whether there is a proof of density Hales-Jewett which gives you good bounds. Now I'm talking a bit in the abstract. What is this density Hales-Jewett theorem? And I told you I'm not going to formulate. There's a corollary which can be seen as an improvement of Semeredi's theorem, and in some sense captures some of the difficulty in this statement. And so what we get is that in Semeredi's theorem, so we get these progressions inside the set A, and we can say something else about the common gap N, the common difference N. So here's the statement. If you just tell me the density and the length of the progression K, then there exists some R. So again, only depends on those two things. And then for any set A with density at least delta, and for any R numbers whatsoever, I can always find a progression in A where the common difference is the sum of some of those R elements. So when you use, for those who know how to do this, you use Hales-Jewett to prove Van der Waerden or density Hales-Jewett to prove Semeredi. You'll get with the same argument this corollary. Actually, this corollary was proved earlier by Furstenberg and Katz-Nelson, but that's not the point here. Okay, so any questions so far? Right. So another direction that results using ergodic theory went in was to polynomial configurations. This is a famous result of Bertelsen and Leibman, where they obtained a polynomial version of the multidimensional Semeredi theorem. And so here is a corollary. This is how it's usually stated, but this is just a special case. The polynomials could have rational coefficients, and there's multidimensional versions. But this is the gist of it. If you have a set with positive density, then you contain this sort of polynomial progressions. Pi of n now are just arbitrary polynomials, let's say with zero constant term. So if p sub I of n is just I times n, we recover Semeredi's theorem. We could take I times n squared. So you have Semeredi's theorem where the common difference is a perfect square. But in fact, you can take any range of polynomials. And so this theorem, this corollary, still doesn't have, in full generality, proofs with which don't use ergodic theory. So then, in 1999, Bertelsen and Leibman, they obtained the polynomial extension of the Hales-Jewett theorem. This is the coloristic one. This time around, Walters found a combinatorial proof within a year. There's some reason for this. So Bertelsen and Leibman used topological dynamics to prove this, but some argument to be made that they don't really use topological dynamics. They dress up a combinatorial argument in topological dynamics. But so in any case, they found the statement, at least by thinking dynamically. And what this leads to, this slide, I hope, is to a natural conjecture, which is a density version of the polynomial Hales-Jewett, or perhaps a polynomial extension of the density Hales-Jewett. There's some argument which of these think about it. So I won't tell you the formulation because it's a bit technical. Polynomial Hales-Jewett itself involves set polynomials which are hard to digest. So I'll just point out the corollary of this conjecture, also a conjecture. So a special case of density polynomial Hales-Jewett, which is very similar to the corollary I gave up here. So I wrote it here for a quadratic single recurrence. You can probably see how to generalize it. But so here's the statement. Just in terms of the density delta, is there an R such that any set with density at least delta, and for any R numbers, I can find a square difference in A where the n comes as the sum of some of those R numbers. So density polynomial Hales-Jewett is one of the major open problems in, well, I would say ergodic Ramsey theory, maybe Ramsey theory in general. But as I said, the statement is kind of difficult to even understand. And so I don't think many people have even attempted to work on it. So I wanted to advertise this conjecture as something maybe easier to think about and still open. All right, so this was sort of an introduction of the 20th century ergodic Ramsey theory. So So as I said, throughout some of these statements have now non-ergodic proofs. And some of those non-ergodic proofs, in fact, give some sort of good bounds. And so here's a non-exhaustive list, actually very incomplete list of people who worked in this direction. So take some of these Ramsey theoretic statements we know are true thanks to ergodic theory. And can we find reasonable bounds for how these variables depend on one another? And one thing you'll notice in common is none of these proofs use ergodic theory. So in fact, don't do it. So I won't say I don't know much, in fact, about bounds. Yeah, so this is where the limit of what you can do with ergodic theory. Right. So let's talk about dynamics again. So I need just a couple of definitions. The topological dynamical system for us will just be a compact metric space. You can think of a circle or a finite set, and then a homeomorphism. If you want a circle, you can take a rotation, for instance. And the measure preserving system is just a topological dynamical system then that has a measure, probability measure, which is invariant under the dynamics. So this is what we mean here by being invariant. We usually take pre-images, but I'm making everything invertible, so it doesn't matter. Take a set A, you apply the transformation, should have the same measure. Okay, that's it. That's all the ergodic theory. So what are examples of these things? So the examples we care about in ergodic Ramsey theory come from sets of integers. And they come via construction we call Furstenberg's correspondence principle. Furstenberg used this construction to convert Smeredis theorem and other Ramsey theoretic statements into problems about ergodic theory. So here's how it goes. So you give me a set A of natural numbers. First thing I do, I will look at its indicator function. It's now a string of zeros and ones. Extend it the zeros to the negative integers. Because I want an invertible system, I need negative integers as well. And so I consider this map. So this is the space of all sequences of zeros and ones. And I consider a map from that set to itself. It just left shifts the sequence. And so it's not hard to see that this is a compact set, compact metric space. It is a homeomorphism. And therefore, when I take here the orbit closure of A, so I take the point A, I apply the left shift, I apply it again and again and again and again. Then I take the closure of all this set of points. This X itself is going to be a compact metric space, and T is a homeomorphism of this space. So that's a topological dynamical system. So this is called the topological Furstenberg system of A, and it encodes dynamically some of the properties from A. Now, this is not yet the end of the story. If we want to prove things like Smeredis theorem, we need our measure preserving system. And so the measure will also come from A as follows. I take the point A, I put Dirac point mass at A, and then I apply T to A, I shift it, I put another Dirac point mass there. I do it again and again and again over a large period of n, and I just average these point masses. So we have some finitely supported measure, that's mu sub n. Oops. That's mu sub n. And because the orbit of A will be dense in my space X, these measures, the sum of these measures is sort of becoming dense in the space X as well. So then when we take a limit here of the mu sub n's, we obtain a measure which is invariant under the homeomorphism T, and therefore we get our measure preserving system. Now, I put quotations here to remind you that this limit may not exist, and there's a little bit going under the hood there. As to subsequences where the limit exists, exactly which subsequence we choose may influence a bit what kind of properties of the set A we are encoding in the system, but let's just pretend limits exist. All right, so we have a measure preserving system, and how do we connect information from that system back to information about A? So we take the cylinder set E of, that's this set here. So all these sequences that are 1 at the 0th coordinate, just some subset of X. And you can check directly from the definition, the set A is recovered as exactly the set of times n when our point A enters this cylinder set E. This follows immediately. And if you choose your subsequence appropriately, the measure of the set E is exactly the upper density of A. And in fact, we have this inequality for any finitely many shifts of A. And so using the correspondence principle, Furstenberg reduced the theorem in the first slide, which contains the Meredith theorem, to this multiple recurrence. So it's essentially the same statement, but now we are on a measure preserving system. So things are a bit easier to work with. And so this measure is always smaller or equal than the density of the corresponding thing involving shifts of A. So this theorem implies the one about in the first slide. So I should say something. In the first slide, I had this question whether some lim-inf can be made into a limit. And as I was writing the slides, I realized I don't know how to answer that question. I know how to answer the question I'm going to ask about measure preserving systems, but yeah, this conversion between the dynamics and the measure, that there's some passing to subsequences, which is not entirely clear. So in any case, so this is the theorem Furstenberg proved, and it leads then to the question, can this lim-inf be turned into a limit? So more generally, we ask this for the k-bounded functions on a measure preserving system. And then we construct these non-conventional ergodic averages, as they are called. Does this sequence of averages converge in L2 as n goes to infinity? Okay, so maybe this seems now like too much ergodic theory. Why do we care? But as we will see, I think by the end of this slide, turns out that this question and the answer to this question was very relevant in additive combinatorics ever since. So right, so I will also point out the case k equals 1 of this theorem is classical, is due to von Neumann. It's called von Neumann's ergodic theorem. So we know it converges, we know exactly where to. And the case k equals 2 was proved by Furstenberg in his paper on Meredith theorem. So he asked, can we prove this for any k? And so there was initial work being done by Konz and Lezin, as we heard from Ben yesterday, and by many other people in between until 2005, when Host and Krag gave a full proof of this question. And there was a separate proof given shortly after by Ziegler. So this was really a problem many people were thinking about ergodic theory. And so very, very roughly speaking, their proof consists of upgrading Furstenberg's structure theory, which involved these distal systems, whatever they are, to nil systems, which are a more structured, a smaller class of systems. And so Host-Kra tell us those are the only systems we need to consider if we are interested in these types of averages. So to give a little bit more detail, they introduced some sort of semi-norms, on bounded functions on the measure preserving system. I see here they are suspiciously similar to Gauer's norms. I should point out they didn't write the norms in this form. They described them in terms of integrals on the cubic measures, but they are equivalent to these expressions, and these should look suspiciously similar to Gauer's norms. That apparently they were arrived at independently from the work of Gauer's, which was, of course, already out by this point. And so just to finish the story here, so the proof then, or the answer to the question, consists of two steps. The first one is quite simple comparatively. So if the norm of a function is 0, then you can use this van der Korput, or you would call it Cauchy-Schwarz type process, to conclude that the average goes to 0. And then the hard part is to show that if the norm is positive, then the function f must correlate with something. I'll call it a nil function. More precisely, it's a continuous function on the Romehl factor of the system. All right, but so this, so especially this second statement then was influential in the inverse conjecture for Gauer's norms, which is now the inverse theorem. And so this is why I was saying that this question and the answer to this question, which again, it's purely an ergodic theoretic interest question, has ramifications in well, now higher order Fourier analysis and additive combinatorics. So one thing I want to call attention to is, while these norms are suspiciously similar to Gauer's norms, they are not exactly the same. So there are differences between them that we understand. And so in that sense, even though you know, you would think, looking at this statement, one should immediately conjecture the inverse theorem for Gauer's norms. I think that's really, there's quite a leap in there, because they do behave differently. So the fact that the Gauer's norms have the same type of inverse theorem is still quite surprising, even in view of this result. So to explain a bit more the distinction here, so if you give me a bounded function now on the integers, on the natural numbers, we can do a Furstenberg correspondence principle thing with this function, and we realize it in some measure preserving system, and then we can evaluate the host CRA norm on the system. And when we translate that all the way back down to the integers, so we arrive at this host CRA norm for the function f. And yeah, so here I have this average over all integer x, which technically means you average over some Faulkner sequence where the limits exist. It's too confusing, you can ignore that. So we take some average here. The point is we take a limit in here before we start averaging in n. And for comparison, the Gowers norms, we sort of have n, the vector n and x in the same range. If you're wondering about this, we need to truncate f to only allow values up to n and then normalize things. But my point is here in the host CRA regime, the variable x is much, much larger than the variable n. And in the Gowers regime, they are of comparable size. This really introduces differences between. So an example, if we look at the Liouville function, so this is a completely multiplicative function. It's -1 at the primes, and so it's counting the parity of prime divisors of n. So Green and Tau proved that the Liouville function is uniform of every order. So in the sense that the Gowers norm goes to 0 for all k. But the same question for the host CRA norm is still open. And in fact, if we could prove that the host CRA norm of lambda goes to 0, then an argument of Terry Tau would tell us that logarithmic Chalo conjecture holds. So it's open and perhaps quite far from what we can prove. So there is quite a distinction between the two norms. Any questions so far? Okay. So this statement here will actually come back a few times, but let's change topic for now. I want to, so this is sort of the how ergodic theory and additive combinatorics sort of got married, but I want to talk about now some applications of this. All right, so here's a question that was asked by Erdős and Graham. Is the Pythagoras equation partition regular? If you finitely color the natural numbers, can you always find x, y, and z of the same color satisfying that equation? So there's some monetary price attached to it. And I was just hearing earlier, if you solve any problem with a monetary value, you should definitely ask Tom Bloom to pay you. I think the price here was given by Graham and not by Erdős, or often. In any case, so there's been some progress on this recently that does not involve any ergodic theory. So for two colors, we now know that the answer is yes, there's always a solution. And this was verified with the computer-aided search in 2016. This proof was, so it was very long. There was some 200 terabytes of data that came out of this. And so some newspapers as far as Portugal were hailing this as the longest mathematical proof ever written by a computer. So take from that what you want, but I think what that means is for three colors, we will never know if we rely on a computer search. And then a more theoretic result is the theorem of Chow, Lindqvist, and Prendeville, which show that if you don't, if you have enough variables in your equation, for instance, if you have a 5-variable version of the Pythagoras equation, then it is partition regular. This using some transference principle and some very interesting arguments that are not ergodic theory. So when two ergodic theorists look at this problem, they decide that it's too difficult. Let's make it a bit easier. Can we find a solution to this equation where perhaps two of the variables have the same color? So Frantzikinakis and Host asked this in 2013, and they were working on this question. And then they realized if we use ergodic theory to address this, we soon arrive at a relation between this problem and the space of completely multiplicative functions that take values in the unit circle. So very roughly speaking, what you do, you use a multiplicative variant density, and then use Furstenberg correspondence for this multiplicative action, at which point you have an action of this group, multiplicative rational numbers, and then you use something called Bochner-Herglotz theorem or spectral theorem, which forces you to look at the Pontryagin dual of that group, and that's where these completely multiplicative functions come from. If you want to answer question 2, you need to understand multiplicative functions. That's the punchline of this discussion. And so what they did prove is that if you have an aperiodic completely multiplicative, they only need a multiplicative function. So any aperiodic multiplicative function taking values in the unit circle, it is in fact Gauer's uniform of every order. So special case of this statement is when f is the Liouville function, which was a statement we had in the previous slide. And in fact, their proof adapts the proof of that case with some extra. I should also say, so to prove this theorem and the special case of the Liouville function, one needs to use the inverse theorem for Gauer's norms to reduce it to a statement about equidistribution on Hill systems, and then one needs to understand how these things equidistribute on Hill systems. And these days there's this argument of double C cat I, which really makes it easier to deal with the multiplicative function. I should say easier. Yeah, by the way, so a function is aperiodic if it averages to 0 in every infinite progression. There are some multiplicative functions that are periodic, these are the Dirichlet characters. And so for those, you won't get this expression, this won't go to 0. And if it doesn't go to 0, the function cannot be cannot be Gauer's uniform. So this is definitely a necessary condition. Okay, so it turns out they didn't quite, so Francekinakis and Host weren't quite able to answer question 2. By the way, this I realize now I have 2013 here, 17 there. This is the same paper, but there's a gap between the archive and the published version. So they weren't able to answer question 2 because you really need to understand all multiplicative functions, aperiodic or not. And so they had a way to deal with non-aperiodic functions, but for whatever reason, it couldn't quite answer question 2. They were able to say something similar, but for this equation. So it always has solutions where x and y have the same color. So I understand Alexei Klurman will maybe tell us more about this problem, so I don't want to spoil his talk, and I will change topic now. But so this is, yeah. Right. So another conjecture that has been very influential in the last few years in ergodic theory and number theory, it is conjecture of Sarnak. So he says that if Xt is our topological dynamical system, which is deterministic, or it has 0 entropy, then orbits coming from this system should be orthogonal to the Liouville function. So Sarnak may use the Mobius function, but I like the Liouville function a bit better. So this is the statement. Now, what does it mean for a system to have 0 entropy? I wrote the definition here. It's not a good definition, but it's the shortest one I could find. The vague idea is that the system is somewhat structured enough that if points are nearby, they tend to stay nearby for some period of time, and some sort of quantitative description of that. Right, and so the motivation for this conjecture, or maybe there's more than one, but so there was an older conjecture of Chaulle, which I mentioned earlier, which I would say I would describe as saying that if you do your correspondence principle with the Liouville function, you end up with a Bernoulli shift. You end up with a measure preserving system where you essentially have IID random variables. This is a conjecture of Chaulle, and Furstenberg had proved that any Bernoulli shift is orthogonal or disjoint from every zero entropy system. And so using a similar idea, Sarnak was able to derive this conjecture from Chowla's conjecture. So this is one of the reasons we expect this to be true. And one of the reasons why zero entropy appears here. And another reason is that we have some examples of systems where this conjecture holds. So the case where X is just a finite set, and we just rotate on a finite set, then the statement is true. And it's in fact equivalent to the prime number theorem in arithmetic progressions. And so this is also true when X is, say, a rotation on a circle, or more generally, any nil system. And this was obtained by Green and Tao in 2008. This was one of the ingredients that go into showing the Liouville function is Gauer's uniform, in fact. And so there's also the class of distal systems, which I keep mentioning, and I won't define it. So they always have zero entropy, so Sarnak's conjecture should apply to them, but the conjecture is still open. If we had never improved Furstenberg's structure theory to Host-Krafft structure theory, we would be trying to prove Sarnak's for distal systems, and we still don't know how to do that. Is that the question? All right, so as I said, there was a lot of work. I won't list all of it, but maybe the highlight is this theorem of Franzikinakis and Host. They had a few results. This is just a special case. It says that if you have your system with zero entropy, and if it has a unique invariant measure, then essentially Sarnak's conjecture holds with the minor, well, I don't know how minor. So you need to be a bit more flexible in your averaging. So you use logarithmic averages, which I think I'm not, I can try it here. I've seen them before. So this just means, yeah. So it just means you're weighting each term A of n with weight 1 over n, and then to make things fair, so that the average of the constant one is roughly 1, you normalize by 1. So if the Shizaro limit exists, then the logarithmic average will also converge to the same value, but the converse is not true. So this is a bit weaker than what Sarnak asked for, but for many purposes, well, yeah, for some purposes, it's good enough. Right. So this proof actually combined a lot of the results in the area from Host-Krafft structure theory. It used something about strongly stationary systems, which I haven't mentioned. But it also used some input from number theory, namely an identity due to tau, which is proved using this entropy decrement argument. And so it turns out these sort of identities or ideas, when they appear, if you can convert them into a statement that you can fit into ergodic theory, which is exactly what Franzikinakis and Host did here, then you can combine it with known techniques in ergodic Ramsey theory and prove. They use it to prove this theorem. So one corollary of this, if you don't care about zero entropy dynamical systems or don't understand exactly what that means, so here's a corollary of their work. It's not a corollary of this theorem, so this is a bit misleading, but it follows from the same proof technique. So if you take an irrational number alpha, and you take this sort of expression that you would care about in Chowla's conjecture, but then you rotate it by alpha, then they can show these averages go to 0. And so this is also true if instead of this linear phase, if you put quadratic phases or any nil sequence in here. That's because nil systems have zero entropy. So so this obviously leaves open the question, what about rational alpha? And at first, it would appear that rational alphas can only be easier than irrational alphas. But I will just point out that alpha when alpha is an integer, this is the hardest scenario. That's Chowla's, well, logarithmic Chalice conjecture.
I mean, in this corollary, we don't have any uniformity on alpha, right?
No. I mean, so what do you mean uniformity?
Like the rate of convergence obviously has to depend on alpha.
I don't know, but yeah,
Otherwise, it would follow for rational
I
alpha.
see. I see. So right, okay.
I think, but at any rate, I don't see. I'll ask another question. I'll ask
Yeah,
later, yeah.
It's a good question. I don't know the answer, but yeah, maybe. Okay, well, what's next? All right. So yeah, I'm changing topics again. So this was interactions with number theory. So there are some other questions in Ramsey theory that we can handle with ergodic methods. So I'm just putting another theorem up here. It's arguably less well known than Semeredi's theorem, but it's also very influential. It's theorem due to Heinemann. And he showed that if you finitely partition the natural numbers, you can always find a monochromatic IP set. An IP set is just the name of these finite sum sets. So you take an infinite set, arbitrary infinite set. All those numbers must be of the same color, but then you can start taking sums. If you sum 2 elements, 3 elements, any finite number of elements of your set, all those sums should still have the same color. And so that's the theorem of Heinemann. And Erdős liked this theorem, and he wanted to find a sort of a density version of this. Now, we cannot be too naive if the set of odd numbers cannot contain an IP set, because you take 2 numbers in B with the same parity, their sum will be an even number. But Erdős asked, what if we allow a shift? We take a set of positive density. If it is the odd numbers, you shift it by 1, you get a set of even numbers. So does every set of positive density add a shift which contains an IP set, one of these sum sets? And so this is true for if you have a finite set B, arbitrarily large but finite. This follows if you use ergodic theory from just Poincaré recurrence theorem iterated and the correspondence principle, but you can prove it just using this as well. But it turns out that this is false for infinite B. This was an example due to Strauss, and I wrote the example here, but yeah, so what's the idea of this example? So if you have an IP set, as I said earlier, you take 2 numbers in B of the same parity, the sum is even. You can use a similar trick to show that an IP set contains a multiple of K for any given K. And this set A has the property that when you shift by any N or any T, you're missing out all the multiples of a given, of some number K. And so this shift of A cannot possibly have an IP set. Then you still need to convince yourselves that this set has positive density. If I wrote it properly, it will have quite high density. And you can already see from this example, you can make the density of A be not just positive, but arbitrarily close to 1. Density of A is equal to 1, then actually it does contain IP sets. Okay, so actually Erdős wrote after this example came out that he wanted to find some density version of Heinemann's theorem. But he made some conjectures, and so these conjectures are now results. So this is a theorem of myself, Florian Richter, and Robertson. So if the set A has positive density, then it will contain the sum of 2 different sets B and C. So here we have twice as many degrees of freedom in some sense. And then so the second conjecture, which we've now also proved, joint with Moreira and Richter and Robertson, that if A has positive density, then it contains this sort of restricted sum set. So all the sums of all pairs of elements from this infinite set B. And so the proof of the first theorem, it was inspired by ergodic theory, but it wasn't really an ergodic theoretic proof because we struggled a bit to use the correspondence principle correctly. And then, yeah, there was a subsequent proof by Host who just used purely ergodic theory and was 5 times shorter than our proof. Ergodic theory still wins, I think. But then to prove the second theorem, it was really not clear how to do it for a while. And it turned out that what we ended up doing was to give a different proof of the first theorem that was more robust and that allowed us to prove something else. And then the second theorem came as a sort of bonus. So the bigger theorem we proved in this line of work is the following. So if you have a set of positive density, it contains not just the sum of two infinite sets, but it will contain the sum of k infinite sets. And so I think I have time to draw a picture here. Just to explain why this has anything to do with dynamical systems, if we have some sort of, this is my set A, and I have some dynamical system and some point here, and then I have this sort of picture. So let's say if this makes any sense. So I want to come in this way by using times from the set B, and then if I come downwards by using times from the set C, I always arrive at an element of A. So if I add a time in B with a time in C, I am inside A. Now, why do I have two paths to go from B to C? What does this mean? It turns out that the sum of two sets B and C is really the union of two different sets. I have all the sums B plus C where B is smaller than C. And I also have all the sums B plus C where C is smaller than B. And dynamically speaking, these two sets sort of behave independently. And this is not just dynamical. So any way you think about this problem, you quickly start to realize you need to consider those two regimes separately. And the difficulty then is to make sure that they agree. Then we go in separate ways. We first apply B or C and then the other set, and we arrive at the same point at the end. And so that's what happens for B plus C for two summons. If you have K summons, you'll have a K-dimensional cube. And then there's no reason to expect this, but it turns out that the way to handle these dynamical objects is to use the same sort of cubic measures, cubic structures that Host and Krah developed when they were trying to answer Rustenberg's question about convergence of averages. So in a way, we were just lucky that all this theory had already been developed and was available to be used in this situation. So we now have this conjecture that so our B plus B theorem can also be extended to more and more summons. So if we have a set with positive density, there should be an infinite B, and the sum of any K elements of B should all be inside A. And the same way that this theorem with different summons is related to cubes, or dynamical cubes at least, if I want this sort of B plus B situation, the dynamical picture is in terms of progression. So I can maybe show again. So now I have, there's only one way to go is by adding elements of the set B again and again and again. So this would correspond to B plus B plus B plus B. Anyway, and so luckily, on top of understanding cubes, there's a lot of ergodic theory that arises from trying to understand progressions. People are worried about. And so we think we can use the same, similar ideas and what is known about progressions in the dynamical context to answer this conjecture. So it's a conjecture, but we have a plan on at least how to deal with it. And so then we made an even bolder conjecture, which we want to think of as the true density version of Heinemann's theorem that Erdős was searching for. So we can take not just some of K elements of B, but any number of elements of B up to K. So if we have here if instead of k we go up to infinite, then this is an IP set, and we know the answer is false. But it's possible that if you fix k in advance, then we can always find this configuration in a shift of. And yeah, so similarly, we have some at least ideas how to deal with this, but we haven't yet finished the proof. And so this actually opens the door to many other questions related to this, involving infinite sets and configurations in Ramsey theoretic context involving infinite configuration. So we actually wrote quite a long list of questions, and this is one of my favorite ones. So if you color, so it's about colorings, there's no density. If you color the natural numbers with finitely many colors, can you always find a sum, a full unrestricted sum of b and m times b for some m? So it's not so difficult to see that if you give me m in advance, I can construct a coloring that rules out some b, including m equals 1, which is the easiest case. But I couldn't construct a color that rules out all of m's, and when you start to construct these colors, it seems to have some relation to the multiplicative properties of natural numbers and how it interacts with the additive property. So I think this question could be quite interesting to see answered, unless there's some color someone comes up with tomorrow that defines a counterexample. But okay, and so another question is, we call it a conjecture due to Granville. He wrote a paper that made the statement. So it's a conjecture of him that the primes contain a sum set b plus c, where b and c are infinite sets. And this is also very interesting conjecture. So for instance, just the fact that primes contain b plus c, where b is infinite and c has 2 elements, this is already equivalent to Zhang's bounded gaps between primes theorems, in 2013. And so similarly, the case where b is infinite and c has k elements for some arbitrary large k, this follows from work of Polymath and Maynard. So these are known, but these are relatively recent and deep results. And so can we make C infinite? And so we don't have an answer for this yet. And I should mention Granville proved this conjecture conditionally on the Dixon-Hardy-Littlewood tuples conjecture. So this is some collection of finite patterns that the primes should contain. And this is, well, I think it's widely believed to be true. And so using that conjecture, we can derive this one. And so using more or less similar methods to what Granville had, you can in fact show that so conditionally on this Dixon-Hardy-Littlewood prime tuples conjecture, primes or primes minus 1 should contain this sort of almost IP set or truncated IP set. And again, if k goes to infinity, then this is a genuine IP set, and we know the primes minus 1 do not contain this creature, but perhaps up to k, or if you believe the Hardy-Littlewood conjectures, then it does contain 1 up to k. You can put here primes plus 1 as well. Okay, and so there's one more result we know of. It was proved last year by Howe and Ziegler that we do have, there do exist infinite sets B and C, where the sums with b smaller than c are contained inside the primes. So it's once again we see that b plus c really needs to be decomposed into these 2 regimes, where b is smaller than c and b is greater than c. Right, and so this theorem combined sieve theory from Maynard's work with a bit of Ramsey theory and correspondence principle. So I think this is my last slide, so yeah, I will stop here now. Thank you.